All right, guys, next piece. With what we want to do here, we want to look at a couple different examples. You're still going to need to implement Elastic Net NR. So one of the ways we're going to talk about doing this is we need to select tuning parameters. How we're going to do that? Well, we're going to do that using cross-validation. And we've talked about how to use cross-validation in other classes, so I'm not going to worry about that. But what I am going to talk to you about is an implementation in a very specific package. It's called the GLMNet package. It's probably the fastest package that exists to do this, and it's the most commonly used one. I will guarantee this package. Like, that's how confident I am. There's two professors from Stanford and a professor from Washington who are responsible for it, and they're really, really good. The idea of this is very, very straightforward. We need to check every lambda alpha combination. So it's all different. It has different coefficients. It has different estimates. So what we really need to do is select the lambda and alpha, that's the model, and use something we compare anything that is predictive to it. For our first example, we're going to use the Longley data. Just to see what the method will do, I just want to give you an example to get a feel for this. Since we only have 16 data points, we're going to use fourfold cross-validations. 4 in each. We'll use cv.glmnet function to perform and fit these methods. So the first thing I'm going to do is I'm just going to set my seed. I'm going to sample 1 through 16. I'm going to rep the folds, and then I'm just going to set the folds 1 through 4. Okay? All these folds are doing is trying to do something. Okay? Here's what we're going to do. For cv.glmnet, we're going to do as.matrix Longley 1. You've got to deal with matrices in glmnet. It's the only thing it knows how to deal with. So this is my response. Or these are my predictors. This is my response. My lambdas are a sequence from 0.01 to 1 by 0.01. So I'm saying here's a set of possible lambdas we can use. I'm going to use fourfold cross-validation where the fold IDs I've preset. Now these fold IDs make sure you can compare different methods over different times. And then here's what you see. You see, okay, here's the mean squared error for log lambda. As it moves across, what it comes out to be. Here's your mean squared errors. Here's what they looks like. Here's what it looks like. These are your predicted errors. Okay. Here's the mean square error for this coefficient. Now, when I come back in here, here's what it says. It says based on everything I've given it, if I just look at the coefficients for the minimum lambda, here's what I get. Okay. Here's what I get. Now, here's what I get. I'm going to get this piece right here. I'm going to get this model. There's no hypothesis testing in this model, but what you're seeing is it did automatic variable selection. It tells you the year coefficient is 0. This is where that lasso and ridge properties start to mix together. You get these predictions, but what you see is year does not matter, okay? Now, as we come back down, let's look at what happens if we just let it go through its process, and we'll see what we get. It comes back down here. It does it again. By default, alpha is set equal to 1. By default, alpha is set equal to 1, which means it's lasso. So what we come down here and what we get is it's coming back and it's telling us, hey, look, if we let it use its pre-specified sequence, it tells us the minimizer has population and year both gone. Now, what we need to figure out how to do is we need to figure out how to select. Now, what it'll do is it'll select the minimum. If the minimum's on the boundary, it'll take the minimum. That's all it cares about. Now, you guys can come back up here and look at it and say, hey, wait a second, the minimum's way down here. That's the reason sometimes specifying what this is important. But it has a preset, and that's fine. It can create insight. Now, if we let it use the preset, it tells us population and employed are both not the variables we want to deal with, and years in the model. So right there's two different candidate models. But this does nothing to tell us how we compare alphas. So what we've got to do is we've got to write a short little script to compare alphas. What I did was I set alpha from 0 to 1, count by 0.01. And I'm going to say keep the minimum CV as rep 0 length alpha. The CV outs are a vector. I'm going to initialize a list of length alpha so I can keep them all. And then what I'm going to do is I'm just going to calculate cv.glmnet for each alpha, and then what I'm going to do is I'm going to calculate the minimum cross-validation. So what I'm doing is I'm storing every alpha in the CV outs. I'm storing the result of the cv.glmnet from every out. So I'm storing all those models so I can keep those, and then I'm keeping the minimum cross-validation. By storing the minimum cross-validation, what I can do is I can find the minimum cross-validation, find the model it corresponds to, and then predict, right? So set everything up that way. And finally, what we're going to do is we're going to go in, we're going to take the minimum cross-validation, we're going to go pull the cross-validation out and call it CV try. And what we're going to do is we're going to get this prediction. And what you see is the best model says don't remove any variables. The coefficient should estimate low, but don't remove any variables. That's not going to be your best predictive model. If you come up here, this is only one possible predictive model. These both models have alpha equal to 1. When we search the lambda and alpha space, what it says is alpha is going to exist and lambda is going to exist from a predictive standpoint such that we don't remove any variables from the model. We use all the variables, and here's the best predictive out of the subset we gave it. So what this script did was it caused us to learn the best model. That's the entire idea. What we're going to do is we're going to send these models out. They're going to find insights. They're going to find these coefficients. But what we do is we set our criterion to say, this is what we define as a good model. Go find it and bring it back. It goes and finds it. It brings it back. Here's the best predictive model. So when you're using this, not only do you have to think about how you select lambda, the model isn't just lambda. The model is lambda alpha. Now, if you're saying I'm using lasso only, that's fine. It's kind of naive. Using lasso by itself nowadays is kind of stupid. It really is. You need to take it beyond that. So when I'm looking at these things, this is what I'm thinking about. To me, this is what it comes out to say. It says, hey, okay, predicting the response here is very key and very crucial to use all these variables. We've tried to get them out, but it predicts better when we don't. Now, again, this is only on 16 data points, so we're going to have to think about what this means and think about how we're going to utilize it. But what you need to continue to think about is what do these lambdas and alphas mean and how do they work? Now, we're going to look at a bunch more examples of this because now that you understand the methodology, it's going to be very useful for us to think about. All right, guys, let me know if you have any questions. Let me know if you need anything.